In this section, we're going to be talking about simple linear regression. Now, if you remember statistics, simple linear regression is a linear regression model with a single explanatory variable. And as you can see from the figure, it is a way to model the linear relationship between two quantitative variables using a line, as you can see here, drawn through those variables, data points. This is known as a regression line. Now, in a linear regression involving two variables, the response variable is the variable being modeled or predicted. In this case, in the figure, quarterly change in GDP. On the other hand, the predictor variable is the variable used to predict the response. The response variable often responds in some way to change the predictor. In this case, quarterly change in the unemployment rate. In linear regression, the response variable is sometimes known as the dependent variable or output or the outcome. On the other hand, in linear regression, a predictor variable is also called an independent variable or input or covariate. As you can see here from the figure, typically a scatter plot can display all the information of a simple linear regression model. And as mentioned, the response variable goes on the y-axis while the predictor variable goes on the x-axis. The plotted points show the data, and here is blue. Now, each position along the line represents where one would expect y to be given a particular x, based on a linear relationship. If you recall, a lot of times, the simple linear regression model can be summed up in the following equation: y equals m times x plus b plus epsilon, which typically is a regression error term. Now, when it comes to the regression error, it's a statistical error modeled as a random variable with a normal distribution that has a zero mean and constant variance. I would say easiest thing in the world to explain this is with a example. So I'm going to be using Kaggle again over here, and I'm just going to try to open up the following link. As you can see here, I opened a link to California housing prices, which is the median house prices for California districts derived from the 1990 census. As you can see, there's going to be a few fields: longitude, latitude, housing median, age, rooms, total bedrooms, population, income, median house value, and ocean proximity. This data is a little old, but at the same time, it is relevant. So I'm going to go ahead and click download. And first thing I'm going to do is try to create a scatter plot. I'm going to go ahead and import a few modules and read the CSV file, housing.csv, and load it into the dataset housing, the data frame housing. And for reference, I'm going to be using the following information from the website to make sense of the data. First things first, I'd like to take a quick look at the data. Right away, you can see there's the longitude, latitude, housing median age, total rooms, bedrooms, population, households, median income, median house value, and ocean proximity. So again, the .head function, we're listing the first 5 records. Right off the bat, these values over here don't make too much sense to me, so I'm going to take a look at the description. And sure enough, it's in the median income for households within a block of houses, measured in tens of thousands of US dollars. All right, let's go ahead and convert that value 8.3 and apply a quick function. So what I'm going to go ahead and do here is I'm going to use apply to multiply this value times 10,000 so that I can understand exactly what the median income was. So at that time, in this case, will be 83,252. So let's go ahead and use that function. Perfect. So right now, instead of 8.3, it's 83,252. Next up, what I would like to do is create a pivot table to understand a couple of fields, get a little bit more intimate with the data. I'd like to look at the values when it comes to the median house value, median income, median age, and my index, I would like it to be the ocean proximity. My aggregate function, I want to be the median. So I'm going to go ahead and run this. All right. So as you can see here, from the following function, I created a pivot table, and we can see that when the home is less than 1 hour from the ocean, the house median age is 30, the house value is about 207,000, and the median income is 37,615. Fantastic. So now let's just remember that this was in 1990. Next up, what I would like to do is go ahead and create a scatter plot. So I created some code. Gonna go ahead and paste it, run it, and as you can see here, I was able to create a scatter plot. And sure enough, as denoted in the pivot table, we can see that the house values for properties that are inland are less than the house values for properties closer to the ocean, or even less than 1 hour in the ocean. And last but not least, it seems like houses that are near a bay are typically the ones with the highest values. On the flip side of the argument, as you can see here, as the income increases for the most part, the median income, the home values increase slightly. So a scatter plot was nice, but at the same time, it is a little confusing when it comes to ocean proximity versus house values. So as we've done in the previous lectures, it's probably easier to create a box plot. So I'm going to go ahead and copy some code and create a box. And sure enough, this now starts making a little bit of sense. So right off the bat, you can see that for a house close or at an island, the values seem to be a lot higher than homes that are inland. And as you can see here, you have the minimum and the maximum, and of course you have some outliers here. But for the most part, it seems like a house that's on an island, or near a bay, or near an ocean, or less than 1 hour of the ocean is valued a little bit higher than homes that are inland. And this again was back in 1990 for California. So let's go back to the scatter plot over here. One would ask, well, what if I was interested in determining my intercept parameter estimator and the slope parameter estimator? Well, this can be obtained using the linear regression function from SciPy. Now this function, linear regression from SciPy, takes in two arrays of equal length as input and returns my intercept parameter and my slope parameter and the correlation coefficient R, the p-value for the correlation coefficient t-test, and the corresponding standard error. So again, the correlation R coefficient is a measure of linear association between the two values. R squared is the proportion of that total variance. The p-value is typically my correlation coefficient t-test, if it's statistically significant or not. And last but not least, the standard error is typically the average distance that the observed values fall from that regression line. So first things first, I'm going to import my SciPy module as a state, and I'm going to create a model equals to linear regression, x and y. Now x and y I'm going to have to define. So in this case, x is going to be my median income and y is going to be my median house value. And if you recall from what we talked about earlier, the response variable goes on the vertical y-axis while the predictive variable typically goes on the horizontal x-axis. So in this case, median income will be my predictor variable and my house value will be my response variable. And of course, last part over here, do a quick check. It's not negative. It's equals to. And looks like I have a quick error. Makes sense. I did not spell it correctly. So I'm going to go ahead and fix that. All right, that is fantastic. I was able to figure out my slope parameter estimator, my intercept parameter estimator, my correlation coefficient R, my p-value, and the corresponding standard error. That is beautiful. So what I'm going to go ahead and do is I'm going to paste some quick code to plot this new regression line to my scatter plot, and voila, we're able to create a linear regression involving two variables, the response variable and the predictor variable. In this case, home values versus income for homes in California. So over here, I'm going to try to go for another example. I'm going to be using a different data set, whereby I'm going to be creating a list. One column will be the size of the house, and the other column will be the price of that home. Now, based off of these lists that I created, I'm going to create a data frame, and I'm going to look at the data frame that I just created. Excellent. Now the next step, what I'd like to do is import my matplotlib.pyplot as plot module. I'm going to create a subplot. Number of rows equals 1. Just going to create 1. So columns equals 1. Going to create a figure. Size 5, 4. Speed things up. Add and pasted the code. So what I'm going to go ahead and do is create a scatter plot. X-axis will be size. Y-axis going to be price. My label is going to have to be modified. All right. Excellent. So now I created a scatter plot of the points that I just created based on the list size and price. Now there are so many different ways of determining the linear regression parameters. So I'm going to use one of them right now. Of course, I'm going to import numpy as np. And as you've seen in the past, I'm also going to import scipy. So the next step, I'm going to say x equals np array size, and my y going to be price. Now I would like to determine my slope and my intercept by using the following function, polyfit x comma y comma 1. Now this is the least squares polynomial fit, where x has to be in an array-like shape. Y has to also be an array-like shape. I'm going to use 1 here as a degree of the fitting of the polynomial. Last part, I'm going to print m and b. Right off the bat, I was able to determine my slope and my intercept. Another way is to use my linear regression function from SciPy. And as you can see here, the slope is 40.8, intercept 190,318, matches this value. And of course, I have my other coefficients. So in this case again, correlation coefficient, which is a linear association between the two variables, my p-value, 0.005, which is my correlation coefficient t-test. Last but not least, my standard error. So now here's a cool trick. I'm going to be using a poly one-dimensional method to estimate unknown values. So I'm going to copy really quick code up here, same model. And now this is where the fun begins. Let's use a different cell, predict, numpy, poly 1D, model. Let's create a input variable called input size. Determine, let's say we have a house size 2,000 square feet. Let's attempt to predict the price of that home. Excellent. $271,000. Wonderful. So now, by using the linear regression, I was able to determine and predict what the price is of a house with size 2,000 square feet. Now, if I change this, say 5,000 square feet, $394,000. Now, one would ask, well, is there a nice way of plotting it on a scatter plot? And the answer is absolutely. So what I'm going to go ahead and do is I'm going to copy and paste some code. I would like my linear regression to be from 0 to about 3,000 square feet. And I'm going to be using predict, just like I've done over here, to plot my response variable. So I'm going to first create a scatter plot. Second, plot my regression line. Color red. There we go. Awesome. So if we go back over here, and we go back over here, as you can see here, now we have a regression line layered on top of a scatter plot. This is great. So let's use a real-world example. I have a data set with San Diego home prices ranging from February 2012 to February 2021. So I created some code to create a scatter plot. So over here, I'm going to go ahead and paste real quick. Nothing too extravagant, just creating a subplot using my date time, my sales price. So it's date time is my x-axis, sales price is my y-axis. Just a few little tricks to clean up the scatter plot when it comes to the formatting of the ticker. And as you can see here, create a line plot over here, just a single line. And as you can see from the data, starts from 2012 and ends April 2021. And this is actually true, accurate historical data. Now the last part, let's try to plot a regression line. I'm going to uncomment a few lines. So we've used this before, model. We use the polyfit method and the poly 1D and create a quick lambda function to create a single regression line column. And last part, plotting my also date time on the x-axis and my regression line on the y-axis. And as you can see here, now with the code above, I was able to create a regression line that's layered on top of actual data, historical data of San Diego median sale price of homes from the year 2012 to 2021. That is pretty cool. We were able to plot our regression line on top of our time series plot. This is great stuff. We were able to use our linear regression function from SciPy. We were able to use a couple of methods from NumPy, PolyFit, and Poly1D. And last but not least, we were able to use pandas, and we were using Matplotlib in this section. Fantastic. This concludes this section.